Welcome back, everyone, to the second part of the electrical bond graph solver. So we're going to go through and we're going to create the state space equation for this bond graph. Well, we have three different junctions here. Two of those junctions are common flow junctions, or where the current is the same around these junctions. And one of these junctions is the common voltage junction, where the voltage summation around these junctions is the same. So what we're going to do is we're going to effectively say we want to find the common flow variable for this junction. Well, you know the causality stuff that we did earlier. Why did we do it the way that we did it? Well, as you can see here, what's supplying the common source of force into this junction? It is this right here, this source of force. So what is the common flow around that junction? It's very simple. It is going to be whatever this SF, the source of flow, is, because the causality is pointing there. There's no arrow there. So the common flow right there into the one junction is effectively going to be just, yes, you guessed it, I. But we don't just use current in these junctions. We want to break it down into a derivative of time, which is equal to current. And that is effectively going to equal charge. The derivative of charge is, with respect to time, is current. The rate of change of charge with respect to time is current. Awesome. So we know what this variable is for this one junction. We actually don't even have to worry about these resistances, simply because we already have a flow for that junction, for the state space equations. Next, we're going to go on to the other junction, the zero junction. And the zero junction is a source of effort. We're going to focus on the causality with the source of effort, right? And the causality with the source of effort, right, is that capacitor right there. You can see we have that right there. In the zero junction, that's important, right? That line right there, the source of effort, right? So we're going to go through and we're going to say, well, what does a capacitor have, right? Well, a capacitor has a charge, right? What's the relationship between charge and capacitance? Well, you can tell right now that we can just put Q2 dot arbitrarily as the flow, and then we're going to say that the integral of that Q2 over C, charge over capacitance, is equal to voltage, right? And you can actually Google this and see if this is the case, but remember that charge over capacitance is equal to voltage, right? And since this is the effort variable right here, we're going to go copy that to the other nodes that are going into the zero junction, simply because it's a common effort junction, right? So Q2 over C. Now we found that variable for that zero junction, right? Which is great. That's the common effort variable, Q2 over C, right? Next, what we want to do is we really want to go through and do this other junction, the last junction right here. And remember how I said that you should put the causality on the component side for effectively an element that's an inductor. Well, you'll see why. And it actually makes our life super easy when you do this. And the reason is because we can assign this value right here to be the common flow in this junction. It's going to be the flux linkage. It's very interesting. The rate of change of flux linkage is equal to voltage. However, not too important right there. It's going to be the flux linkage over L, which is actually equal to charge. So the flux linkage, as I said, the rate of change of flux linkage over time, which is the derivative of flux linkage, is equal to voltage. So we have our source of effort, we have our source of flow. And we know that our source of flow is going to be equal to all the components, because this is a one junction based on this inductor right here. So I'm going to go through and I'm going to put the flux linkage, which is lambda over L, on all these junctions, right? So effectively, that's the charge, right? Given the charge over time, which is the current. Given that we have the current, how do we find the voltage for a resistor? Well, it's resistance times the current, right? And so that effectively solves our problem right there in trying to determine how we're going to figure out what that value really is, right? And then next, Next, what we're going to do, right, is we're going to go through and we're going to say, awesome, that's great. We want to find the capacitance. Well, we can't integrate this. So I'm going to give this the rate of change of charge. I'm just going to assign that value arbitrarily. That makes our life easy because then we can just integrate this function and we're still in the one-dimensional space when it comes to derivatives, right? So let's go through and let's sum up all our equations and see if we can simplify this thing um, and hopefully make our lives a lot easier, right? I'm going to put Q1 right here to simplify things. So let's just say Q2 dot is equal to Q1 dot, right? Mm, because Q1 dot is so I'm going to take these junctions and I'm going to sum them together, right? And so in this first equation, we see Q1 dot is going into the zero junction. So we're going to say Q1 dot is positive. Next, we're also going to see that Q2 dot is going out of the system. So we're going to say Q2 dot. Why am I summing the Q1s and not the Q2Cs? Well, you'll see if you sum these values, you'll just get 0. And why is that? Well, everything has a common effort within a zero junction, so you have to sum the flows to get your value, right? So we have Q1 dot minus Q2 dot minus this flux linkage over the inductance is equal to 0, right? And so that's pretty cool. We already know what Q1 dot is. It's I, right? So let's substitute back in I for this equation since we haven't actually used Q1 dot in any of the situations or scenarios, right? So we're going to say I minus Q2 dot minus lambda over L is equal to 0. And let's solve for this first order differential equation right here, Q2 dot. Then what we're going to do is we're going to say Q2 dot is equal to lambda over L minus I, which is the current. So we have our summation for that variable right there. The second one that we want to look at is lambda dot. What is lambda dot? Well, we can actually sum together these junctions right here and for the effort. And we know the effort variables here are going to be these ones, and these ones, right? And so we can create the state space equations, and we also have one more actually, this one, the input to the junction. So that equation is going to be the sum of all the efforts in this junction, right? All the efforts in this junction that are going to be lambda dot is going out of the junction. What's also going out of the junction is this resistance value, lambda R3 times lambda over L. What else is going out of the junction is the Q3 over C2. And what's coming into the junction is Q2 over C1. And that's all equal to 0, right? So then we solve for lambda, and what do we get? We get Q2 over C1 minus R3 lambda over L minus Q3 over C2 equals lambda dot. We have one more variable we want to solve for. What is Q3 equal to? Well, we arbitrarily set Q3 equal to lambda over L. And you have to do this because you can't necessarily have a representation that integrates this function, right? So you can't really integrate this and have some sort of representation in a one-dimensional differential equation. It's really hard to do. So we arbitrarily set that value, and that's easy to write because Q3 dot is equal to, and we have it right up here, lambda, which is the flux linkage, over L. So we have our three state space equations, 1, 2, and 3. So effectively what we can do is, what are the state variables? The state variables are Q2, Q3, and lambda right here. And what are our equations? Well, lambda dot is equal to Q2 over C1 minus R3 lambda over L minus Q3 over C2 is equal. Yeah, well, we already know what it's equal to because I already said it's equal to on the other side. Okay, the next one is going to be Q3 dot equals lambda over L. And the last and final equation is going to be Q2 is equal to lambda over L minus an I, right? And then we can put this in matrix form by stating we have Q2, Q3, lambda, and these are all dots. The derivative, the rate of change, is equal to this matrix right here. So it's going to be 0 right there because do we have any Q1s in Q2? Or do we have any Q2s in Q2? No. When I look at this equation, do we have any Q2s in Q2? No. When I look at this equation, there's no Q2s in that equation. Right? Do we have any Q3s in Q2? No. So that's another thing. Do we have a lambda? Yeah, we do. We have a 1 over a lambda, actually. So that's going to be a 1 over a lambda in Q2, right? And I might have done the math wrong here a little bit. I did the math wrong here, right? Solving for Q2, when you look at it, it's going to be negative minus I. So we need to actually switch that out to Q2 dot is equal to I minus lambda over L. So we need to actually switch these out right here, which is going to be equal I minus lambda over L. Right? These things are hard, right? And we need to keep track of them. So 1 over L, negative 1 over L right there. Same thing for Q3. Do we have anything for Q3 and Q2? No. Nothing there too, but we do have a lambda. We have a 1 over an L right there. And then the last in the lambda function, do we have a Q2? Yeah, we do. What do we have? A 1 over C1. What else do we have for Q3? Do we have a Q3? Yeah, we do. Minus 1 over C2. And then for the R, what do we have? Well, we factor out the lambda that we get negative R3 over L, right? And then what we can do is we just have to put our variables here, Q2, Q3, lambda, right? And do we have any constants? Yeah, we do. We have that I right there, so we need another matrix to resolve those. So in Q2, we do have an I. I'm going to put a 1 there. I'll put a 0 in the other ones. And then this one's just going to be, if I can squeeze it in, an I right there. And that is your state space equation for this problem. Hopefully you find that helpful in trying to identify how to make that state space equation. And I hope to see you in the next video.